Hello there, and welcome to a gentle journey through the cosmos. I'm so grateful you found your way here tonight. Perhaps you've had one of those days that seem to stretch endlessly, or maybe you're simply someone who finds peace in the quiet mysteries that drift above us each evening. Either way, you've arrived at exactly the right place. Tonight, you have nothing to do but rest. Let your thoughts settle like dust on an ancient surface, your breathing slow to match the rhythm of distant orbits, and your body grow as light as if you were floating in the weightless embrace of space itself. Because tonight, we're not just looking up at the moon, we're drifting through its story, discovering the gentle secrets of our closest celestial companion. For over 4.5 billion years, this silver guardian has watched over Earth, shaping our tides, stabilizing our seasons, and casting its soft glow across countless sleeping souls. But beneath its familiar face lies a universe of wonder. Ancient collisions that birthed worlds, water hiding in eternal shadows, and gravitational dances that have choreographed the very rhythm of life on Earth. We'll explore these mysteries together, wandering from the moon's violent birth to its peaceful influence on our daily lives. From hidden ice deposits to the precise mechanics that keep our planet steady in its cosmic waltz. Some of what you hear tonight may surprise you, or at the very least spark gentle curiosity as you drift towards sleep. And just before we begin, if these calm explorations help you find peace at the end of your day, consider supporting this channel. It helps other restless souls discover this quiet corner of the universe, one peaceful night at a time. Now, let's begin our moonlit journey. The moon was born from one of the most spectacular collisions in our solar system's history. Picture, if you will, the early Earth 4.5 billion years ago, a molten world still finding its shape in the young solar system. Into this primordial scene came Theia, a wandering planet roughly the size of Mars, hurtling through space on a collision course with our nascent world. When these two bodies met, the impact was so tremendous that it vaporized portions of both planets, sending massive clouds of molten rock spiraling into space. This wasn't a gentle merger, but a cosmic catastrophe that reshaped everything. The debris from this collision, a mixture of material from both Earth and Theia, began to dance in orbit around our battered planet. Slowly, patiently, gravity gathered these scattered pieces together, condensing them into the glowing sphere that would become our moon. This same violent birth also gave Earth its tilted axis, the gentle lean that brings us our seasons and makes our planet a more dynamic, livable world. The evidence for this dramatic origin story lies not in ancient texts or fossils, but in the rocks themselves. When Apollo astronauts brought back samples of lunar soil and stone, scientists discovered something remarkable. The moon's composition closely mirrors Earth's mantle, as if the two worlds shared a common ancestry. The oxygen isotopes in lunar rocks match those found on Earth with uncanny precision, suggesting they formed from the same primordial materials. But perhaps most telling is what the moon lacks. Unlike Earth, our satellite contains very little iron in its core, consistent with the idea that it formed from the lighter materials blasted away during that ancient collision. The heavier elements, including most of the iron, remained with Earth, while the moon inherited the scattered remnants of two worlds torn apart and reformed. Modern computer simulations can now recreate this cosmic collision with stunning detail. Scientists adjust variables like the strength of the colliding bodies, the angle of impact, and the temperature and pressure conditions, watching as virtual worlds crash together in digital space. These models suggest that the moon may have formed much more quickly than once thought, perhaps condensing from the impact debris in a matter of hours rather than centuries. The simulations show material being launched directly into stable orbits around Earth, creating a satellite that begins its existence already at a safe distance from our planet's gravitational embrace. This rapid formation helps explain some of the Moon's puzzling characteristics, including its unusual orbit and the distribution of materials across its surface. Today, the Moon drifts through space at an average distance of 238,855 miles from Earth. To put this vast distance in perspective, you could fit nearly 30 Earth-sized planets in the space between our world and its companion. Yet despite this enormous gap, the Moon's presence shapes our daily lives in ways both obvious and subtle. Its gravitational pull creates the tides that rise and fall along our shores twice each day, following a rhythm that has persisted for billions of years. But the Moon isn't standing still in this cosmic dance. Each year, it moves approximately 1.5 inches farther from Earth, a gradual recession that speaks to the dynamic relationship between our two worlds. This slow retreat means that the Moon we see today appears larger in our sky than it will for future generations. In the distant past, when the Moon was young and much closer to Earth, it would have dominated the night sky as a looming silver giant, creating tides far more dramatic than anything we experience today. As it continues its gradual journey outward, driven by the same tidal forces that move our oceans, future astronomers will look up at a smaller, more distant Moon. Eventually, this recession will make total solar eclipses impossible, as the Moon will no longer appear large enough to completely cover the Sun's disk during their celestial alignment. The precision of the Moon's orbital mechanics has served as humanity's first clock and calendar. Its 27-day journey around Earth provided our ancestors with a reliable way to measure time, dividing the year into lunar months that still influence our calendars today. The Moon returns to the same position relative to the Sun every 29.5 days, creating the familiar cycle of phases that has guided human activity for millennia. Farmers have planted and harvested by moonlight, sailors have navigated by its position, and countless cultures have built their religious and social calendars around its predictable rhythms. The discovery of water on the Moon represents one of the most significant revelations in recent lunar science. For decades after the Apollo missions, scientists believed our satellite to be a completely dry world, a lifeless sphere of rock and dust where water could never exist. The soil samples brought back by astronauts showed no trace of moisture, leading to the conclusion that the Moon's surface was utterly barren. This understanding persisted for nearly 40 years, until new missions began to paint a very different picture of our celestial companion. The first hints of lunar water came from an unexpected source, India's Chandrayaan-1 mission in 2008. This robotic explorer detected hydroxyl molecules scattered across the Moon's surface, concentrated particularly near the polar regions. The discovery was revolutionary, suggesting that water might exist in forms and places previously thought impossible. Subsequent missions, including NASA's Lunar Reconnaissance Orbiter and the LCROSS Impact Experiment, confirmed and expanded upon these findings, revealing a Moon far more complex and dynamic than anyone had imagined. The most dramatic confirmation came in October's Stratospheric Observatory for Infrared 2020, when NASA astronomy detected actual water molecules on the Moon's sunlit surface. This wasn't just the hydroxyl groups discovered earlier, but genuine H2O molecules existing in one of the harshest environments in the solar system. The water was found in Clavius crater, one of the largest impact features visible from Earth, hiding within tiny glass beads or tucked into microscopic spaces between mineral grains. The concentration was sparse, roughly equivalent to a 12-ounce bottle of water distributed across a cubic meter of soil. But its very presence challenged everything scientists thought they knew about how water behaves in the vacuum of space. Even more remarkable are the permanently shadowed regions near the Moon's poles, cosmic refrigerators, where ice has remained frozen for billions of years. These areas, hidden in the depths of ancient craters, never received direct sunlight due to the Moon's nearly upright orientation, relative to the Sun. Temperatures in these shadowed valleys plunge to negative 250 degrees Celsius, colder than the surface of Pluto and cold enough to preserve water ice for eons. Radar observations have revealed vast deposits of frozen water in these regions, estimated at over 600 billion kilograms of ice, enough to fill hundreds of thousands of Olympic swimming pools. The water in these permanently shadowed regions tells a story of cosmic delivery spanning billions of years. Some arrived aboard comets, those dirty snowballs from the outer solar system that occasionally swing close to the Sun and crash into planetary surfaces. Other water molecules formed through the interaction of solar wind with the Moon's rocky surface, as hydrogen atoms from our star combined with oxygen locked in lunar minerals. Over time, these water molecules have migrated across the Moon's surface, bouncing from place to place until they've found refuge in the perpetual darkness of the polar regions, where they've remained frozen in time like ancient libraries of cosmic ice. This hidden water represents more than just a scientific curiosity. It's a potential resource that could support future human exploration of the Moon and serve as a stepping stone to deeper space missions. Water can be broken down into hydrogen and oxygen, providing both rocket fuel and breathing gas for astronauts. It can also serve as radiation shielding and, of course, as drinking water for lunar bases. The discovery has transformed the Moon from a dead world into a potential oasis, a place where human civilization might one day take root among the stars. The Moon's gravitational influence reaches far beyond the creation of tides, acting as a cosmic stabilizer that keeps Earth's climate relatively steady over geological time. Our planet's axis is tilted at 23.5 degrees, giving us our seasons as different hemispheres lean toward or away from the Sun throughout the year. But this tilt isn't perfectly stable. Without the Moon's gravitational anchor, Earth would wobble chaotically, its axis shifting dramatically over relatively short periods. This stabilizing influence has been crucial for the development and maintenance of life on our planet, preventing the extreme climate swings that would make complex ecosystems nearly impossible to sustain. The relationship between Earth and Moon creates a gravitational tug-of-war that affects both worlds. While the Moon pulls on Earth's oceans to create tides, our planet's much stronger gravity deforms the Moon itself, causing its solid surface to flex by several inches twice each day. This tidal flexing generates heat within the Moon's interior, contributing to geological processes that might otherwise have ceased billions of years ago. The same tidal forces that create this deformation are also responsible for the Moon's synchronous rotation, the phenomenon that keeps the same face always pointed toward Earth. This tidal locking occurred early in the Moon's history, when it was still much closer to Earth and the tidal forces were far stronger than they are today. The Moon's rotation gradually slowed until it matched its orbital period exactly, creating the stable configuration we observe today. As a result, there is a near side of the Moon that faces Earth and a far side that remained hidden from human eyes until the space age. This hidden hemisphere, often incorrectly called the dark side, receives just as much sunlight as the near side, but was completely unknown until Soviet spacecraft first photographed it in 1959. The far side of the Moon reveals a landscape dramatically different from the familiar near side. Where the Earth-facing hemisphere is marked by large dark plains called Maria, the far side is heavily cratered and mountainous, telling a story of ancient bombardment preserved in stone. These differences arose because the Moon's crust is thicker on the far side, making it more difficult for ancient lava flows to reach the surface and create the smooth plains visible on the near side. The far side also experiences a different environment, completely shielded from Earth's magnetic field and radio emissions, making it an ideal location for sensitive astronomical observations. Recent missions have revolutionized our understanding of the Moon's composition and structure. The James Webb Space Telescope, while primarily focused on distant galaxies and exoplanets, has also contributed to our knowledge of the solar system, including discoveries related to other moons in our cosmic neighborhood. These observations remind us that moons are common throughout the solar system, with Jupiter and Saturn hosting dozens of these satellite worlds, each with its own unique characteristics and mysteries. The moon's phases create a celestial rhythm that has guided humanity since the dawn of consciousness. As our satellite journeys around Earth every 29.5 days, we witness the gentle transformation of its illuminated face, from the invisible new moon through the growing crescent to the brilliant full moon, and back again through the waning phases. This cycle occurs because we see different portions of the moon's sunlit hemisphere as it travels its orbital path. During the new moon, our companion passes between Earth and the sun, hiding its illuminated face from our view entirely. Then, night by night, a slender crescent appears and grows, like a cosmic smile emerging from the darkness. The first quarter moon presents itself as a perfect half circle, dividing the lunar disk into light and shadow with geometric precision. This phase arrives roughly a week after the new moon, marking the halfway point in the satellite's journey around our planet. As the days progress, the illuminated portion continues to expand, creating the waxing gibbous phase, where more than half, but not quite all of the visible face, glows with reflected sunlight. Then comes the full moon, that magnificent moment when Earth, moon, and sun align in perfect opposition, allowing us to see the entire near side bathed in golden light. After the full moon reaches its peak brilliance, the cycle reverses, with the illuminated portion gradually shrinking through the waning gibbous phase. The last quarter arrives another week later, again showing us a precise half circle, but now the opposite side is illuminated compared to the first quarter. The waning crescent follows, growing thinner each night until it disappears entirely, returning to the new moon phase and beginning the cycle anew. This eternal dance of light and shadow has inspired countless myths, poems, and songs throughout human history. What makes this cycle even more remarkable is its precision. The moon's phases occur with such regularity that they served as humanity's first accurate calendar, allowing ancient civilizations to predict seasonal changes and plan agricultural activities. The word month itself derives from moon, reflecting this fundamental connection between our satellite cycle and human timekeeping. Even today, many cultural and religious observances follow the lunar calendar, maintaining an ancient connection to the rhythms of our celestial companion. The same gravitational forces that create Earth's tides also shape the moon's own subtle movements through space. Our planet's gravity doesn't just hold the moon in orbit, it continuously deforms our satellite's shape, stretching it slightly along the line connecting the two worlds. This tidal bulge is small, amounting to only a few inches, but it demonstrates that even solid rock yields to the inexorable pull of gravity across the vast distances of space. The moon, in turn, raises tides not just in Earth's oceans, but in the solid ground beneath our feet, causing the entire planet to flex by several inches twice each day. These tidal forces create a complex rhythm in Earth's rotation. The friction generated by tidal movement gradually slows our planet's spin, making each day slightly longer than the one before. This effect is imperceptibly small in human terms, adding only about 1.5 milliseconds to the length of a day every century. But over geological time, this cumulative effect is profound. Billions of years ago, when the moon was young and much closer to Earth, our planet spun much faster, and a day lasted only a few hours. The fossil records of ancient coral reefs preserve this history, showing growth patterns that reflect the shorter days and different tidal rhythms of the distant past. The moon's surface bears the scars of billions of years of cosmic bombardment, creating a landscape unlike anything found on Earth. Without an atmosphere to burn up incoming meteors or geological processes to erase impact craters, every collision is preserved like a fossil in stone. The largest of these impact features, visible even to the naked eye, are the dark plains called Maria, Latin for seas. These aren't bodies of water, but vast fields of ancient lava that filled enormous impact basins between 3 and 4 billion years ago. The Maria formed during a period known as the Late Heavy Bombardment, when asteroid and comet impacts were far more frequent than they are today. Massive objects, some hundreds of miles across, slammed into the moon with such force that they cracked the crust and allowed molten rock from deep within to flow to the surface. These lava flows cooled and solidified into the dark basaltic plains we see today, creating the familiar features that form the face of the man in the moon, or the rabbit on the moon, depending on which cultural tradition shapes your perception. Between these dark plains lie the lunar highlands, ancient mountainous regions composed primarily of a rock called anorthosite. This light-coloured mineral formed during the moon's earliest history, when the entire satellite was covered by an ocean of molten rock. As this magma ocean slowly cooled, lighter minerals floated to the surface while heavier materials sank toward the core, creating the layered structure we observe today. The highlands represent the moon's original crust, battered by billions of years of impacts, but still preserving the chemical signature of our satellite's formation. The Apollo missions brought back samples from both the Maria and the highlands, providing scientists with actual pieces of another world to study in terrestrial laboratories. These lunar rocks revealed surprising details about the moon's composition and history. Unlike Earth rocks, which show evidence of weathering by wind and water, lunar samples preserve their original characteristics with remarkable clarity. They contain no organic materials, no water locked within their crystal structures, and no signs of the geological processes that continuously reshape our home planet. The chemical composition of these samples provided crucial evidence for the giant impact theory of the moon's formation. The rocks showed that lunar material closely matches Earth's mantle in its isotopic ratios, particularly for oxygen, suggesting the two bodies formed from the same source materials. However, the moon's overall composition differs from Earth's in important ways, containing less iron and other heavy elements that would have remained with the larger body during the collision that created both worlds. Beyond the samples returned by human missions, scientists have access to lunar meteorites, pieces of the moon that were blasted into space by asteroid impacts and eventually fell to Earth. These natural samples come from regions all across the moon's surface, providing a more comprehensive view of lunar composition than the geographically limited Apollo and lunar landing sites. The meteorites confirm the story told by the human-collected samples, while extending our knowledge to previously unexplored regions of our satellite. The moon's interior structure remains partially mysterious, hidden beneath miles of solid rock, and accessible only through indirect methods of investigation. Seismic instruments left by Apollo astronauts recorded moonquakes for years after the missions ended, revealing that our satellite is geologically active in subtle ways. These lunar tremors occur primarily when the moon passes closest to Earth in its elliptical orbit, suggesting that tidal stresses continue to fracture rock deep within the satellite's interior. The data from these seismic networks indicates that the moon has a small iron core, much smaller proportionally than Earth's core, but still significant enough to generate weak magnetic fields in some regions of the surface. This core is surrounded by a partially molten layer and then by the solid mantle and crust that form the moon's outer shell. The discovery of this internal structure helps scientists understand how the moon formed and evolved, cooling from its initially molten state into the layered world we observe today. Recent missions have mapped variations in the moon's gravitational field with extraordinary precision, revealing hidden mass concentrations beneath the surface. These gravitational anomalies, called mascons, lie buried beneath many of the large impact basins, representing dense material that was either excavated from deep within the moon during the impact or deposited by the impacting object itself. The mascons affect the orbits of spacecraft flying over them, providing a gravitational map of the moon's hidden interior structure. The moon's magnetic field, though much weaker than Earth's, tells an intriguing story about our satellite's past. Some regions of the lunar surface show evidence of ancient magnetic fields much stronger than anything present today, suggesting that the early moon may have possessed a global magnetic field similar to Earth's. This field would have been generated by convection in the molten iron core, but as the moon cooled and the core solidified, the magnetic field weakened and eventually disappeared. Today, only scattered patches of magnetized rock remain as fossils of this ancient magnetic activity. These magnetic anomalies create miniature magnetic bubbles on the moon's surface, providing slight protection from the solar wind in some locations. While far too weak to shield human explorers, these magnetic fields affect how the solar wind interacts with the lunar surface, potentially influencing the formation and distribution of water molecules in these regions. The study of lunar magnetism continues to reveal new details about the thermal and chemical evolution of our satellite over billions of years. The moon's thin atmosphere, technically called an exosphere, exists in a state so tenuous that it barely qualifies as an atmosphere at all. This gossamer envelope contains fewer particles than the best vacuum chambers on Earth, made up of scattered atoms of sodium, potassium, hydrogen, and other elements released from the lunar surface by solar wind bombardment and micrometeorite impacts. During the lunar day, when temperatures soar to over 400 degrees Fahrenheit, these atoms dance high above the surface before settling back down during the frigid lunar night. The entire atmosphere weighs less than 10 tons, compared to Earth's atmosphere, which weighs over 5 quadrillion tons. In this ethereal environment, sounds cannot travel. The sky remains black even during daylight, and the horizon appears much closer due to the moon's smaller size and lack of atmospheric refraction. Without the protective blanket of a thick atmosphere, the moon experiences temperature swings that would shatter most materials we encounter on Earth. In direct sunlight, the surface can reach temperatures hot enough to boil water, while areas in shadow plunge to colder than liquid nitrogen. These extreme variations occur because there's no atmosphere to distribute heat around the moon's surface, leaving each location entirely dependent on whether it faces toward or away from the sun. The transition between these temperature zones happens gradually as you cross the terminator, the boundary between the moon's day and night sides, where the angle of sunlight changes the surface temperature by hundreds of degrees over relatively short distances. The absence of atmospheric protection means that the moon's surface is constantly bombarded by cosmic radiation and micrometeorites, tiny particles of space dust that would burn up harmlessly in Earth's atmosphere. These microscopic impacts continuously sandblast the lunar surface, gradually wearing down rocks and creating the fine powder that covers much of our satellite. This powder, called regolith, forms a blanket several feet thick in most places, created by billions of years of cosmic gardening. The regolith has a unique texture, described by Apollo astronauts as similar to charcoal or pencil graphite, and it clings to everything it touches due to its electrostatic properties and the lack of moisture to bind the particles together. Within this seemingly lifeless regolith lie traces of the moon's dynamic interaction with space. Solar wind particles become embedded in the surface grains, creating a record of the sun's activity over millions of years. Helium-3, a rare isotope deposited by the solar wind, accumulates in the lunar soil in concentrations far higher than anything found on Earth. This isotope could potentially serve as fuel for future fusion reactors, making the moon a valuable resource for humanity's energy needs. The regolith also contains tiny glass beads formed when micrometeorite impacts melt the surface material, creating spherules that sparkle in the lunar dust like microscopic jewels. The moon's relationship with comets and asteroids extends far beyond simple impact cratering. These cosmic wanderers have served as delivery vehicles, bringing water, organic compounds, and other materials to the lunar surface over billions of years. When a comet approaches the inner solar system, the sun's heat vaporizes its icy nucleus, creating a tail of gas and dust that can extend millions of miles into space. Some of this material eventually finds its way to the moon, either through direct impact or by settling onto the surface as cosmic snow. The organic compounds found in lunar samples while not indicative of life, demonstrate that the building blocks of biology have been present on the Moon throughout its history. The gravitational relationship between Earth and Moon creates phenomena that extend well beyond simple tidal effects. This cosmic partnership generates what scientists call tidal heating within both bodies. Though the effect is much more pronounced on the Moon due to its smaller size and proximity to Earth's massive gravitational field. As the Moon orbits our planet, Earth's gravity continuously flexes and squeezes the satellite's rocky interior, generating heat through friction. This process may experience occasional geological activity, despite help explain why the Moon still being much smaller and older than Earth. The energy from tidal heating could maintain pockets of molten or semi-molten rock deep within the Moon, contributing to the moonquakes detected by seismic instruments. The Moon's influence on Earth's rotation creates a phenomenon called the lunar month recession, a gradual lengthening of the time it takes our satellite to complete its orbit. As tidal friction slowly robs energy from the Earth-Moon system, our planet's rotation slows and the Moon spirals outward to compensate. This process has been ongoing since the Moon's formation, and it will continue until both bodies become tidally locked to each other, with the same face of Earth always pointing toward the Moon, just as the same face of the Moon always points toward Earth. However, this final state lies so far in the future that the Sun will have evolved into a red giant star long before it occurs, fundamentally altering the entire solar system. The study of lunar samples has revealed that the Moon preserves a record of the early solar system's chemical evolution that has been largely erased from Earth's surface. Unlike our dynamic planet, where plate tectonics, weathering, and biological processes continuously recycle surface materials, the Moon maintains an archive of ancient impacts and volcanic activity spanning billions of years. Rocks from the lunar highlands date back over 4 billion years, making them among the oldest accessible planetary materials in the solar system. These ancient stones contain isotopic signatures that reveal details about the composition of the early solar system and the processes that shaped the terrestrial planets during their formation. The precision of modern analytical techniques has allowed scientists to extract remarkable information from tiny fragments of lunar material. Individual mineral grains can be dated with extraordinary accuracy, revealing the timing of specific geological events on the Moon. Some samples show evidence of multiple impact events, with older minerals reset by the heat and pressure of later collisions. This layered history, preserved in microscopic detail within lunar rocks, provides a timeline of the bombardment history that shaped all the inner planets during the solar system's violent youth. The Moon's far side, hidden from Earth's view, presents a landscape that tells a different story from the familiar near side. The far hemisphere shows fewer of the dark volcanic plains that characterize the Earth-facing side, instead displaying a heavily cratered highland terrain that preserves impacts from the earliest epochs of lunar history. This asymmetry reflects fundamental differences in crustal thickness and composition between the two hemispheres, possibly resulting from the Moon's formation process or early geological evolution. The far side's thicker crust made it more difficult for ancient lava flows to reach the surface, leaving the primordial highland terrain largely intact. Recent high-resolution mapping of the lunar surface has revealed features invisible to Earth-based observers, including networks of lava tubes that may extend for miles beneath the Moon's surface. These underground tunnels, formed when flowing lava carved channels through the rock, could provide natural shelters for future lunar explorers. The constant temperature and protection from radiation within these tubes make them attractive locations for permanent lunar bases. Some of these lava tubes appear large enough to house entire cities, with dimensions that dwarf any cave system on Earth. The discovery of these natural underground spaces has transformed thinking about how humans might eventually establish a permanent presence on the Moon. The Moon's role as a cosmic time capsule extends to its preservation of materials from throughout the solar system. Over billions of years, impacts have delivered samples from asteroids, comets, and even other planets to the lunar surface, where they remain preserved in the regolith-like specimens in a museum. Some lunar samples may contain fragments of ancient Earth rocks, blasted into space by massive impacts during our planet's early history, and later collected by the Moon's gravitational influence. These cosmic cross-contaminations create a complex library of solar system materials waiting to be discovered and analysed by future lunar explorers. The Moon's influence on Earth's climate system extends far beyond its role in stabilising our planet's axial tilt. The gravitational dance between our two worlds affects ocean circulation patterns, atmospheric tides, and even the behaviour of Earth's magnetic field. Tidal forces don't just move water, they also create subtle atmospheric tides that influence weather patterns and the distribution of gases in our atmosphere. The Moon's gravity pulls on the entire Earth, including its molten core, potentially affecting the generation of our planet's magnetic field through complex interactions that scientists are still working to understand. The discovery of water on the Moon has opened new chapters in our understanding of how this precious substance behaves in the harsh environment of space. Water molecules on the lunar surface exist in a constant state of flux, sublimating into vapor during the hot lunar day and potentially migrating to cooler regions where they can condense again. This creates a tenuous water cycle, unlike anything on Earth, where molecules may bounce across the surface for thousands of years before finding permanent refuge in the permanently shadowed regions near the poles. The process is so slow and delicate that it operates on geological timescales, gradually concentrating water ice in the coldest, most protected locations on the Moon. The interaction between solar wind and the lunar surface creates an ongoing chemical laboratory where new compounds form through processes impossible on Earth. When high-energy protons from the Sun strike oxygen-bearing minerals in the regolith, they can create hydroxyl groups and even water molecules through direct chemical reactions. This process occurs continuously across the Moon's sunlit surface, though the water produced is quickly lost to space unless it finds shelter in microscopic crevices or migrates to cooler regions. The efficiency of this process varies with the solar wind's intensity and the composition of the surface materials, creating a complex pattern of water formation and loss across the lunar landscape. The Moon's gravitational field contains subtle irregularities that reveal the internal structure and composition of our satellite in remarkable detail. These variations, detected by precision tracking of orbiting spacecraft, show where dense materials lie buried beneath the surface and where the crust is thicker or thinner than average. The gravitational maps created by these measurements reveal ancient impact basins filled with dense volcanic rocks, mountain ranges that extend deep into the crust, and regions where the mantle may lie closer to the surface than elsewhere. This gravitational topography provides a three-dimensional view of the Moon's interior structure that complements the surface features visible to telescopes and cameras. Modern space missions continue to revolutionize our understanding of the Moon through increasingly sophisticated instruments and analytical techniques. Each new mission brings capabilities that surpass previous explorations, from high-resolution cameras that can spot objects as small as a few feet across, to spectrometers that can identify specific minerals from orbit. The cumulative effect of these technological advances has been to transform the Moon from a distant, mysterious world into a complex, dynamic environment that we're only beginning to fully comprehend. Future missions promise even greater revelations, with plans for sample return missions from the far side, permanent robotic observatories, and eventually human settlements that will make the Moon humanity's first stepping stone into the broader cosmos. The story of lunar exploration itself reflects humanity's expanding capability to reach beyond our home planet and touch other worlds. From the first telescopic observations that revealed mountains and craters on the Moon's surface, to the robotic missions that first soft-landed on our satellite, each achievement built upon previous successes and failures. The Apollo program represented the culmination of this progression, placing human footprints on another world and bringing back tangible pieces of the cosmos for study. Now, as we prepare for a new era of lunar exploration, we carry with us not just advanced technology, but also the accumulated wisdom of decades of studying our nearest celestial neighbour. The moon continues to hold secrets that await discovery, from the composition of its deep interior to the full extent of its water resources and the complete history of its magnetic field evolution. Each answered question reveals new mysteries, ensuring that our satellite will remain a subject of scientific fascination for generations to come. As you settle into sleep tonight, know that above you drifts this ancient companion, carrying in its silent journey through space the stories of cosmic collisions, hidden ice, and the delicate gravitational dance that has shaped both our worlds across the vast expanse of geological time. The moon's surface temperature variations create one of the most extreme environments in our solar system, yet this harshness has preserved a pristine record of cosmic history that Earth's dynamic surface has long since erased. During the 14-day lunar day, surface temperatures climbed to nearly 400 degrees Fahrenheit, hot enough to melt lead and boil many liquids we take for granted. But when night falls and lasts for another 14 Earth days, the same locations plunge to negative 250 degrees Fahrenheit, colder than the surface of distant Pluto. This dramatic swing of over 600 degrees occurs because there's no atmosphere to moderate the temperature, no protective blanket to hold in warmth or shield the surface from the sun's intense radiation. The transition zones between these extremes create fascinating thermal landscapes where materials expand and contract with such force that rocks crack and shatter over time. Within these temperature extremes, the moon's regolith behaves in ways that would seem magical on Earth. The fine dust that covers the surface, created by billions of years of micrometeorite bombardment, has properties unlike any earthly soil. It clings to surfaces with surprising tenacity due to electrostatic forces that build up in the airless environment. Apollo astronauts discovered that this dust would stick to their spacesuits and equipment, finding its way into every crevice despite their best efforts to keep it out. The regolith particles are incredibly sharp, having never been smoothed by wind or water, creating an abrasive powder that posed unexpected challenges for both equipment and human explorers. The absence of weathering processes on the moon means that every grain of dust and every boulder tells a story stretching back millions or even billions of years. Unlike Earth, where wind and rain constantly reshape the landscape, the moon preserves the evidence of ancient events with remarkable fidelity. Footprints left by Apollo astronauts over 50 years ago remain as crisp and clear as the day they were made, testament to the unchanging nature of the lunar environment. These human traces will likely persist for millions of years, slowly degrading only through the gentle rain of cosmic dust and the rare impact of small meteorites. The moon's role as a cosmic museum extends to its collection of materials from throughout the solar system. Over the eons, asteroids and comets have deposited samples from distant regions onto the lunar surface, where they remain preserved like specimens in a vast natural laboratory. Some of these materials may have originated from Mars, blasted into space by massive impacts, and eventually captured by the moon's gravity. Others carry the chemical signatures of the outer solar system, bringing water and organic compounds from the realm of the gas giants. This cosmic mixing has created a treasure trove of scientific specimens scattered across the lunar landscape, waiting to be discovered and analysed by future explorers. The discovery of organic compounds in lunar samples initially surprised scientists who expected the moon to be completely sterile. While these carbon-based molecules don't indicate the presence of life, they demonstrate that the building blocks of biology have been present on the moon throughout its history. These compounds likely arrived aboard comets and asteroids, along with water and other volatile materials that have accumulated in the polar regions. The preservation of these delicate molecules in the harsh lunar environment speaks to the moon's role as a deep freeze, maintaining a chemical archive of the early solar system's composition. Recent analyses of lunar samples have revealed trace amounts of elements that provide clues about the sun's evolution over billions of years. The solar wind, that constant stream of charged particles flowing from our star, has been implanting atoms into the lunar regolith for eons. By studying the isotopic ratios of these embedded particles, scientists can reconstruct how the sun's output has changed over geological time. This record shows that our star has been remarkably stable, providing the steady energy source that has allowed life to flourish on Earth. The Moon, in its role as a passive collector of solar particles, preserves this stellar history in microscopic detail within its surface materials. The magnetic anomalies scattered across the Moon's surface create invisible shields that deflect the solar wind in small regions, forming miniature magnetic bubbles that affect how space weathering occurs. These localized magnetic fields are remnants of an ancient global magnetic field that protected the Moon during its early history. When this field existed, it would have created auroras similar to those we see on Earth. Ghostly lights dancing across the lunar sky as charged particles from the solar wind interacted with the magnetic field lines. The loss of this global field marked a turning point in the Moon's evolution, leaving it fully exposed to the harsh radiation environment of space. The Moon's interior structure reveals a world that was once geologically active, but has since settled into relative quiet. Seismic data from the Apollo missions showed that moonquakes still occur, though they're much weaker and less frequent than earthquakes. These lunar tremors happen primarily when the Moon passes closest to Earth in its elliptical orbit, demonstrating that tidal forces continue to stress the interior structure. The moonquakes also reveal that the Moon's interior is partially molten, with a small iron core surrounded by a partially liquid layer that allows seismic waves to travel in complex patterns through the satellite's interior. The gravitational anomalies hidden beneath the Moon's surface tell stories of cosmic violence from the solar system's youth. These mass concentrations, or mascons, represent dense material that was either excavated from deep within the Moon during massive impacts or deposited by the impacting objects themselves. The largest mascons lie beneath the Moon's major impact basins, creating gravitational bullseyes that affect the orbits of spacecraft flying overhead. These gravitational variations were first discovered when early lunar orbiters experienced unexpected changes in their trajectories, leading scientists to realize that the Moon's interior is far from uniform in density and composition. The Moon's synchronous rotation, which keeps the same hemisphere always facing Earth, results from billions of years of tidal evolution. In its youth, the Moon rotated much faster, showing all of its faces to Earth over the course of a day. But the gravitational interaction between the two worlds gradually slowed the Moon's rotation until it matched its orbital period exactly. This process, called tidal locking, demonstrates the power of gravitational forces to reshape celestial mechanics over vast periods of time. The same process is occurring throughout the solar system, with most large moons eventually becoming tidally locked to their parent planets. The far side of the Moon, forever hidden from Earth's view, remained a complete mystery until the space age brought the first photographs from Soviet spacecraft. This hidden hemisphere revealed a landscape dramatically different from the familiar near side, with fewer of the dark volcanic plains and more of the ancient, heavily cratered highland terrain. The differences between the two hemispheres reflect the Moon's complex formation history and the uneven distribution of materials during its early geological evolution. The far side's rugged terrain preserves impacts from the solar system's earliest epochs, creating a fossil record of cosmic bombardment that has been partially erased from the near side by volcanic activity. The Moon's thin exosphere contains atoms that have been knocked loose from the surface by solar wind bombardment and micrometeorite impacts. This gossamer atmosphere extends high above the surface, creating a tenuous envelope of scattered particles that rises and falls with the lunar day and night cycle. Sodium atoms in this exosphere can be detected from Earth using specialized telescopes, creating a faint glow that extends far beyond the Moon's visible disk. During meteor showers, when the Moon passes through streams of debris from comets, the exosphere becomes temporarily denser as impacts vaporize surface materials and add new atoms to the thin atmospheric envelope. The interaction between the solar wind and lunar surface creates ongoing chemical reactions that slowly alter the composition of surface materials over geological time. This process, called space weathering, darkens the regolith and changes its reflective properties, making older surfaces appear different from freshly exposed materials. The rate of space weathering varies across the Moon's surface, depending on the local magnetic environment and the composition of the underlying rocks. Areas with stronger magnetic fields experience less space weathering because they're partially shielded from the solar wind, preserving their original colors and brightness for longer periods. The Moon's role in stabilizing Earth's climate extends beyond its influence on axial tilt to include effects on ocean circulation patterns and atmospheric dynamics. The tidal forces that move our oceans also drive deep water circulation patterns that distribute heat around the globe, helping to moderate Earth's climate. Without the Moon's gravitational influence, these circulation patterns would be fundamentally different, potentially leading to more extreme regional climate variations. The Moon also creates atmospheric tides, subtle pressure variations that affect weather patterns and the distribution of gases in our atmosphere. The discovery of lunar water has transformed our understanding of how volatiles behave in the harsh environment of space. Water molecules on the Moon exist in a constant state of flux, sublimating into vapor during the hot lunar day and potentially migrating to cooler regions where they can condense again. This creates a tenuous water cycle that operates on geological timescales, gradually concentrating ice in the permanently shadowed regions near the poles. The process is so delicate that it can be disrupted by relatively minor changes in temperature or solar radiation, making the lunar water cycle a sensitive indicator of changing conditions in space. The permanently shadowed regions near the Moon's poles represent some of the most extreme environments in the solar system, yet they may also be among the most scientifically valuable. These areas have remained in darkness for billions of years, creating natural laboratories where ancient ice and other volatile materials have been preserved like samples in a cosmic deep freeze. The temperatures in these regions are so low that even normally volatile substances become solid, creating deposits of frozen carbon dioxide, ammonia, and other compounds alongside the water ice. These materials provide a record of the solar system's chemical evolution that extends back to the earliest epochs of planetary formation. The Moon's gravitational influence creates subtle but measurable effects on Earth's solid surface, causing the entire planet to flex by several inches twice each day. This solid Earth tide is much smaller than the ocean tides, but demonstrates that even solid rock yields to gravitational forces across the vast distances of space. The effect is strong enough to be detected by sensitive instruments, and it must be accounted for in precision measurements of Earth's shape and gravitational field. The solid Earth tides also affect underground water systems and may even influence seismic activity in some regions by changing the stress patterns in Earth's crust. The Moon's ancient magnetic field, now largely extinct, once created a protective bubble around our satellite that deflected the solar wind and cosmic radiation. Evidence for this ancient magnetosphere comes from magnetized rocks in lunar samples, which preserve the direction and strength of magnetic fields that existed billions of years ago. The loss of this global magnetic field marked a fundamental change in the Moon's interaction with space, leaving it fully exposed to the harsh radiation environment that continues to alter its surface today. The timing of the magnetic field's disappearance coincides with the Moon's gradual cooling and the solidification of its iron core. The study of lunar samples continues to yield new insights into the formation and evolution of the Earth-Moon system. Advanced analytical techniques can now extract information from individual mineral grains, revealing details about impact events, volcanic activity, and space weathering processes that occurred billions of years ago. Some samples show evidence of multiple heating events, recording a complex history of impacts and geological activity that shaped the Moon's early evolution. These microscopic time capsules preserve information about conditions in the early solar system that has been largely erased from Earth's more dynamic surface. The Moon's influence on Earth's rotation creates a phenomenon that affects timekeeping itself, requiring periodic adjustments to our most precise clocks to account for the gradual slowing of our planet's spin. This tidal breaking has been ongoing since the Moon's formation, and it continues today at a rate that adds about 1.5 milliseconds to the length of a day every century. While imperceptible in human terms, this effect accumulates over geological time, meaning that days were significantly shorter in Earth's distant past. The fossil records of ancient organisms preserve evidence of these shorter days in their growth patterns, providing an independent confirmation of the Moon's role in Earth's rotational evolution. The Moon's surface composition varies dramatically between different regions, reflecting the complex history of impact events and volcanic activity that shaped our satellite over billions of years. The dark volcanic plains, or maria, contain iron-rich basaltic rocks that formed from lava flows during the Moon's geologically active period. In contrast, the bright highland regions consist primarily of anorthosite, a light-coloured rock that crystallized from the Moon's primordial magma ocean. These compositional differences create distinct terrains that tell different chapters of the lunar story, from the violent bombardment of the early solar system to the gradual cooling and solidification of our satellite's interior. The Moon's role as Earth's companion extends far into the future, though the relationship between our two worlds will continue to evolve as tidal forces gradually push them apart. In the distant future, the Moon will appear smaller in Earth's sky, eventually becoming too small to create total solar eclipses. The tidal forces that currently slow Earth's rotation and push the Moon away will continue until both worlds become mutually tidally locked, with the same faces always pointing toward each other. However, this final state lies so far in the future that the Sun's evolution into a red giant star will fundamentally alter the entire system long before this gravitational equilibrium is reached. The Moon's preservation of ancient materials makes it an invaluable archive of solar system history, containing samples and evidence from epochs that have been erased from other worlds. Future lunar missions will undoubtedly uncover new chapters in this cosmic story, from the detailed composition of the far side highlands to the complete inventory of volatile materials trapped in the polar regions. Each new discovery adds depth to our understanding of how planetary systems form and evolve, while also providing practical knowledge for humanity's expansion into space. The Moon stands ready to serve as both a scientific laboratory and a stepping stone for future exploration, carrying within its ancient rocks and hidden ice the keys to understanding our cosmic origins and our destiny among the stars. As we drift deeper into the night, these lunar mysteries continue their ancient dance above us, unchanged by our newfound understanding, yet somehow more wondrous for being known. The Moon that rises tonight carries the same gravitational pull that shaped Earth's first tides billions of years ago, the same surface scars from cosmic collisions that occurred before life took hold on our planet, and the same hidden reservoirs of ice that may one day sustain human civilization beyond Earth. In its patient journey across the star-filled sky, our satellite carries forward the story of two worlds bound together by gravity, time, and the gentle forces that shape the cosmos. Tonight, as you rest beneath this ancient guardian, you participate in a relationship as old as Earth itself, a cosmic partnership that will continue long after we've all returned to the stardust from which we came. The Moon's gravitational embrace reaches beyond the obvious effects on our oceans, creating invisible rhythms that pulse through the solid Earth itself. Twice each day, As our satellite passes overhead, the entire planet flexes and breathes like a living thing. The ground beneath your feet rises and falls by several inches in response to these tidal forces, though the movement is so gradual and gentle that you'll never feel it. This solid Earth tide affects everything from underground water systems to the precise measurements scientists make when studying our planet's shape. Even the most sophisticated instruments must account for this cosmic breathing, this subtle reminder that Earth and Moon remain locked in their eternal gravitational waltz. Deep within underground caves and caverns, the Moon's influence can be measured in the rise and fall of water tables and the slow movement of underground rivers. Spelunkers and cave researchers have long noticed that water levels in some cave systems follow tidal patterns, rising and falling in rhythm with the Moon's position overhead. This underground tidal effect demonstrates how thoroughly the Moon's gravity permeates our world, reaching into the deepest recesses of Earth's crust and affecting systems that seem completely removed from celestial mechanics. The Moon's pull on groundwater systems may even influence the timing of earthquakes in some regions, as changing water pressure affects the stability of underground rock formations. The relationship between Earth and Moon creates what scientists call a binary planet system, two worlds so closely matched in size and gravitational influence that they orbit around a common center of mass. This balance point, called the barycenter, doesn't lie at Earth's center, but rather inside our planet, about 1,000 miles beneath the surface. As both worlds orbit around this invisible point, they create a complex dance that affects everything from tidal patterns to the stability of spacecraft orbits. This binary nature makes the Earth-Moon system unique among the terrestrial planets, with no other world in the inner solar system possessing such a large satellite relative to its own size. The Moon's influence on Earth's magnetic field creates subtle but measurable effects that scientists are still working to fully understand. As our satellite passes through Earth's magnetosphere, it disturbs the flow of charged particles trapped in our planet's magnetic field lines. These disturbances create ripples in the magnetosphere that can affect radio communications and satellite operations. During certain phases of the Moon's orbit, when it passes through specific regions of Earth's magnetic tail, these effects become more pronounced, creating what researchers call lunar magnetic wake effects. The interaction demonstrates how thoroughly interconnected the with influences Earth-Moon system remains, flowing both ways between our two worlds. The study of lunar laser ranging, where scientists bounce laser beams off reflectors placed on the Moon by Apollo astronauts, has provided some of the most precise measurements in all of science. These experiments can detect changes in the Earth-Moon distance accurate to less than an inch, revealing not only the Moon's gradual recession, but also subtle variations in Earth's rotation and the effects of climate change on our planet's shape. When ice sheets melt or groundwater is depleted, the redistribution of mass affects Earth's rotation rate and shape in ways that can be measured through these lunar ranging experiments. The Moon serves as a cosmic surveyor's benchmark, allowing scientists to track changes in Earth's physical properties with extraordinary precision. The Moon's role in Earth's climate system extends to influences on wind patterns and atmospheric circulation that operate on both daily and seasonal timescales. Atmospheric tides, created by the Moon's gravitational pull on our planet's gaseous envelope, generate subtle pressure waves that ripple around the globe twice each day. These atmospheric tides are much weaker than ocean tides, but still measurable with sensitive instruments. They affect the distribution of gases in the atmosphere and may influence weather patterns in ways that meteorologists are still investigating. The Moon's gravitational signature can be detected in barometric pressure readings taken at weather stations around the world, a testament to the far-reaching effects of our satellite's presence. The thermal properties of lunar rocks reveal a world where temperature changes propagate through solid material at an almost leisurely pace. During the lunar day, heat penetrates only a few inches into the surface before the sun sets and begins its 14-day absence. This shallow heating zone means that just beneath the surface, temperatures remain relatively stable, creating an insulating layer that protects deeper materials from the extreme temperature swings above. Apollo astronauts drilling core samples discovered that even a few feet below the surface, temperatures remain nearly constant, hovering around -20 degrees Fahrenheit, regardless of whether the surface above is baking in sunlight or freezing in shadow. The moon's regolith contains a hidden treasure trove of rare elements concentrated through billions of years of solar wind bombardment. Helium-3, deposited grain by grain as charged particles from the sun embedded themselves in the lunar soil, accumulates to concentrations thousands of times higher than anything found on Earth. This isotope could potentially fuel fusion reactors with minimal radioactive waste, making the moon a valuable isations. The Reggie energy resource for future civilolith also concentrates other rare elements delivered by the solar wind, creating a natural ore body that represents millions of years of cosmic mining operations. Each handful of lunar soil contains atoms that traveled 93 million miles from the Sun to reach their final resting place on our satellite, E's surface. The interaction between cosmic rays and the lunar surface creates a continuous shower of secondary particles that contribute to the space weathering process. High-energy particles from distant stars and galactic events strike the moon's surface with tremendous force, breaking apart atoms and creating new isotopes not found in the original rocks. This cosmic ray bombardment gradually alters the chemical composition of surface materials, creating isotopic signatures that can be used to determine how long rocks have been exposed at the surface. The process works like a cosmic clock, with the accumulation of rare isotopes providing a timeline for geological events that shape the lunar landscape. The moon's far side presents a landscape that preserves the most ancient impacts in the solar system. Craters formed during the final stages of planetary accretion over 4 billion years ago. These impact scars tell the story of the late, heavy bombardment, a period when massive objects regularly struck the inner planets with devastating force. The far side's heavily cratered terrain remained largely unmodified by later volcanic activity, creating a fossil record of this violent epoch that has been partially erased elsewhere in the solar system. Each crater represents a chapter in the story of solar system formation, from small asteroids that created simple bowl-shaped depressions to massive impactors that excavated multi-ring basins hundreds of miles across. The discovery of glass beads in lunar samples revealed evidence of ancient fire fountains that once erupted from the moon's interior. These tiny spherules, formed when volcanic gases propelled molten droplets high above the surface, tell of a time when the moon was geologically active and capable of spectacular displays of volcanism. The glass beads contain trapped gases that provide samples of the moon's ancient atmosphere, a thin envelope that existed briefly during periods of intense volcanic activity. Some of these beads contain water molecules, confirming that volcanic processes once brought water from the moon's interior to its surface, where it was quickly lost to space in the airless environment. The moon's influence on tidal phenomena extends beyond Earth's oceans to affect the solid surfaces of other worlds throughout the solar system. Jupiter's moon Europa experiences tidal flexing so intense that it keeps a subsurface ocean liquid beneath miles of ice, while Saturn's moon Enceladus shoots geysers of water into space due to tidal heating. These examples demonstrate the fundamental role that gravitational interactions play in shaping planetary systems, with tidal forces serving as engines of geological activity and potential harbingers of life. The Earth-Moon system provides a template for understanding these processes, showing how gravitational relationships between worlds can persist and evolve over billions of years. The moon's synchronous rotation creates a unique acoustic environment where seismic waves travel differently than they do on Earth. Without an atmosphere to carry sound waves, vibrations travel only through solid rock, creating patterns of seismic propagation, unlike anything experienced on our planet. The moon rings like a bell when struck by large meteorites, with seismic waves reverberating through its interior for hours after impact. This acoustic signature reveals details about the moon's internal structure that complement other methods of studying our satellite's hidden layers. The different way sound travels through the moon reflects its unique geological history and current state of internal cooling. The preservation of impact glass on the moon's surface provides a record of cosmic collisions that spans billions of years. When meteorites strike the lunar surface, the intense heat and pressure of impact melts rock and soil, creating glass that preserves the exact moment of collision. This impact glass contains microscopic fragments of the impacting objects, providing samples of asteroids and comets that would otherwise be impossible to study. Scientists can analyze these tiny inclusions to learn about the composition of objects throughout the solar system, turning the moon into a vast collection of meteorite samples delivered by natural processes over geological time. The moon's weak magnetic field creates miniature magnetic anomalies that affect how the solar wind interacts with specific regions of the surface. These localized magnetic bubbles, remnants of ancient magnetic activity, deflect charged particles and create unique space-weathering patterns in their vicinity. Some regions protected by magnetic anomalies retain their original brightness longer than surrounding areas, creating a patchwork of different surface colors visible in high-resolution images. The study of these magnetic variations provides clues about the moon's thermal history and the processes that once generated its global magnetic field billions of years ago. The lunar maria represents some of the largest volcanic features in the solar system. Vast plains of hardened lava that filled enormous impact basins during the moon's active period. These dark regions formed when the moon's interior was still hot enough to produce molten rock that could flow to the surface through cracks in the crust. The lava flows that created the maria were incredibly fluid, spreading across hundreds of miles to create the smooth plains we observe today. The composition of maria rocks differs significantly from highland materials, reflecting the chemical evolution of the moon's interior as heavier elements sank toward the core and lighter materials rose to the surface. The moon's role in Earth's rotational stability extends beyond preventing chaotic wobbling to include effects on the length of seasons and the predictability of climate patterns. Without the moon's stabilizing influence, Earth's axis would wander unpredictably over relatively short geological periods, causing dramatic shifts in seasonal patterns that would make long-term climate evolution nearly impossible. This stability has been crucial for the development of complex life forms that depend on predictable seasonal cycles for reproduction, migration, and other biological processes. The moon's gravitational anchor helps maintain the environmental conditions that allow ecosystems to evolve and persist over millions of years. The interaction between solar radiation and lunar surface materials creates ongoing chemical reactions that slowly transform the regolith over geological time. Solar wind particles implant themselves in mineral grains, while ultraviolet radiation breaks chemical bonds and creates new compounds not found in the original rocks. This space-weathering process gradually darkens the lunar surface and changes its reflective properties, making older surfaces appear different from freshly exposed materials revealed by recent impacts. The rate of these changes varies across the moon's surface, depending on local conditions, creating a complex pattern of surface evolution that continues today. The moon's gravitational field contains subtle irregularities that reveal hidden mass concentrations beneath its surface, legacy features from the most dramatic impacts in solar system history. These mascons, or mass concentrations, represent dense material that either survived the impact process or was deposited by the impacting objects themselves. The gravitational signatures of these buried features affect spacecraft orbits and provide three-dimensional maps of the moon's internal structure. Some mascons correspond to visible impact basins on the surface, while others lie hidden beneath later geological formations, testament to the moon's complex impact history. The study of lunar samples has revealed that the moon experienced periods of intense bombardment interspersed with quieter epochs of gradual geological evolution. The ages of impact glass and shocked minerals in lunar rocks provide a timeline of major collision events that affected not just the Moon, but likely all the inner planets. This bombardment history shows periods when the solar system was filled with debris from planetary formation, alternating with more peaceful times when orbits had stabilized and large impacts became rare. The Moon preserves this record because its surface has not been reshaped by plate tectonics or extensive erosion. The Moon's exosphere responds dynamically to solar activity, expanding when solar wind intensity increases and contracting during quieter periods. This atmospheric breathing reflects the direct connection between the Moon's tenuous atmosphere and the space environment, demonstrating how unprotected worlds respond to changes in stellar radiation. During solar storms, the Moon's exosphere can become temporarily denser as increased solar wind bombardment liberates more atoms from the surface. These variations in atmospheric density affect how the Moon interacts with charged particles and electromagnetic fields in its vicinity. The thermal inertia of lunar materials creates temperature patterns that persist long after the sun has set or risen in any given location. Rocks and regolith heat up slowly during the lunar day and cool down gradually during the long night, creating thermal waves that propagate through the surface at predictable rates. This thermal behavior varies dramatically between different types of materials, with solid rock retaining heat longer than loose regolith. The thermal properties of surface materials can be mapped from orbit using infrared instruments, revealing details about regolith thickness and rock distribution across the lunar landscape. The Moon's role as a gravitational lens affects the orbits of small objects in the Earth-Moon system, creating complex trajectories that can persist for thousands of years. Asteroids and comets passing through this region experience gravitational perturbations from both Earth and Moon, sometimes becoming temporarily captured in chaotic orbits around the system. These quasi-satellites and co-orbital objects demonstrate the complex dynamics of the Earth-Moon gravitational environment, where small changes in velocity or position can dramatically alter an object's fate. The Moon's gravitational influence extends far beyond its physical surface, shaping the trajectories of cosmic debris throughout the inner solar system. The preservation of volatile materials in permanently shadowed regions near the Moon's poles represents one of the most extreme examples of environmental stability in the solar system. These areas have remained in darkness for billions of years, creating natural laboratories where ancient ice and other compounds survive in pristine condition. The deposits contain not just water ice, but also frozen carbon dioxide, ammonia, and organic compounds that provide a record of the solar system's chemical evolution. The study of these materials offers the early epoch's insights into conditions during planetary formation, when volatile compounds were more abundant throughout the inner solar system. The Moon's influence on Earth's ocean circulation patterns extends beyond simple tidal movements to affect the global circulation systems that distribute heat around our planet. The mixing caused by tidal currents helps drive the thermohaline circulation that carries warm water toward the poles and brings cold water toward the equator. Without the Moon's tidal influence, these circulation patterns would be fundamentally different, potentially leading to more extreme regional climate variations and altered patterns of marine ecosystem distribution. The Moon's role in ocean mixing also affects the distribution of nutrients and oxygen in seawater, influencing the productivity of marine ecosystems worldwide. The discovery of ancient zircon crystals in lunar samples has provided some of the oldest direct dates for events in the solar system, revealing details about the timing of planetary formation and differentiation. These tiny mineral grains formed during the Moon's earliest geological processes and have survived billions of years of impact bombardment and thermal cycling. The isotopic compositions of lunar zircons provide constraints on the age of the Moon itself and the duration of the magma ocean period that followed its formation. These microscopic time capsules preserve information about conditions in the early solar system that has been largely destroyed on more geologically active worlds. The Moon's far side serves as a natural radio quiet zone, shielded from Earth's electromagnetic interference by the bulk of the lunar mass itself. This unique environment makes the far side an ideal location for sensitive radio astronomy observations that would be impossible on Earth or in Earth orbit. Future radio telescopes on the lunar far side could detect signals from the cosmic dark ages, the period before the first stars formed, providing unprecedented insights into the universe's earliest epochs. The far side's radio silence represents one of the Moon's most valuable scientific resources, a natural laboratory for studying the cosmos without interference from human technology. The interaction between the Moon's weak solar wind creates a unique gravitational field and the plasma environment in the lunar vicinity, where charged particles flow around the Moon like water around a stone in a stream. This interaction creates a wake region behind the Moon, where the solar wind is partially excluded, forming a cavity in the particle stream that extends far into space. The boundaries of this cavity are marked by enhanced electric fields and particle acceleration, creating a complex electromagnetic environment that affects how spacecraft operate in lunar orbit. The study of these plasma interactions provides insights into how solar wind interacts with airless bodies, the solar system. The Moon's throughout regolith contains microscopic diamonds formed by the shock and pressure of meteorite impacts. Tiny gems created in moments of cosmic violence. These impact diamonds are different from terrestrial diamonds, formed not in the slow geological processes of Earth's interior, but in the instantaneous conditions of hypervelocity collisions. The diamonds preserve information about the impact processes that created them, including the temperature and pressure conditions that existed during the brief moments of collision. Their presence in lunar samples demonstrates the extreme conditions that regularly occur on airless worlds exposed to meteorite bombardment. The gravitational relationship between Earth and Moon creates resonances that affect the orbits of artificial satellites and space debris in the vicinity of our planet. Some orbits become unstable due to these gravitational perturbations, while others remain stable for extended periods. The Moon's influence on satellite orbits must be carefully considered when planning space missions, particularly for spacecraft that remain in Earth orbit for extended periods. These orbital resonances also affect the long-term evolution of space debris, with some objects eventually being perturbed into Earth's atmosphere, while others are flung away into interplanetary space. The Moon's surface bears the signatures of ancient magnetic fields in the form of magnetized rocks that preserve the direction and intensity existed billions of magnetic fields that of years ago. These paleomagnetic records indicate that the Moon, once magnetic field comparable, possessed a global in strength to Earth's current field, generated by convection in a molten iron core. The gradual weakening and eventual disappearance of this magnetic field marks a fundamental transition in the Moon's evolution, from a geologically active world with internal heat sources to the cold, quiet body we observe today. The timing of this magnetic field decay provides clues about the thermal evolution of the Moon's interior. The study of impact crater formation on the Moon has revealed the physics of high-velocity collisions that occur throughout the solar system. The Moon's airless environment and lack of geological activity preserve craters in unconditioned prist, allowing scientists to study the complete range of impact features from simple bowl-shaped craters to complex multi-ring basins. The relationships between crater size, depth, and the properties of target materials provide insights into impact processes that apply throughout to worlds the solar system. These studies help scientists understand the bombardment history of all terrestrial planets and assess impact hazards for future space missions. The Moon's role in Earth's tidal evolution extends far into the future, with the gradual slowing of our planet's rotation and the recession of our satellite, creating a system that will eventually reach tidal equilibrium. In this distant future state, both Earth and Moon would be tidally locked to each other, with the same faces always pointing toward their partner. Days and months would have the same length, and the Moon would remain fixed in the sky above one hemisphere of Earth, while the other hemisphere would never see it. However, this final configuration lies so far in the future that the sun's evolution will fundamentally alter the entire system long before tidal equilibrium is achieved. The moon's influence on the development of a life on Earth may extend beyond its role in climate stabilization to include effects on the chemistry of early oceans and the concentration of essential elements. Tidal pools created by the moon's gravitational pull may have served as natural laboratories where organic molecules could concentrate and interact, potentially contributing to the origin of life itself. The regular cycling of tidal waters would have created alternating wet and dry conditions that could have driven chemical reactions necessary for the formation of complex organic compounds. The moon's role in creating these dynamic environments may have been crucial for the emergence of the first living systems on our planet. The preservation of solar wind particles in lunar regolith creates a record of the sun's activity and evolution over billions of years. The isotopic composition of implanted solar wind atoms varies with solar activity cycles and long-term changes in stellar output, creating a detailed archive of our star's behavior preserved in microscopic detail within lunar soil grains. This record extends far beyond human historical observations and provides insights into how solar variability has affected planetary atmospheres and climate systems throughout the solar system. The moon serves as a passive collector of solar history, accumulating data about our star's past that cannot be obtained through any other means. The moon's gravitational field affects the shape of Earth's atmosphere, creating subtle bulges and compressions that influence global atmospheric circulation patterns. These atmospheric tides are most pronounced in the upper atmosphere, where the thin air responds more readily to gravitational forces. The effects cascade down through atmospheric layers, influencing wind patterns and pressure systems that affect weather and climate. The moon's atmospheric influence operates on multiple timescales, from the twice-daily tidal cycles to longer-term modulations that may affect seasonal weather patterns and climate variability. The chemical composition of lunar volcanic glass provides insights into the moon's interior composition and the processes that brought materials from deep within our satellite to its surface. These glass beads formed when volcanic gases propelled molten droplets high above the lunar surface, where they cooled rapidly in the vacuum of space. The rapid cooling preserved the original chemical composition of the volcanic material, providing unaltered samples of the moon's interior. Analysis of these glasses reveals details about the moon's internal differentiation and the chemical evolution of its mantle over geological time. The moon's surface serves as a natural laboratory for studying processes that occur throughout the solar system on airless bodies. The combination of vacuum conditions, extreme temperature variations, and constant bombardment by cosmic radiation and micrometeorites creates an environment that tests materials and systems in ways impossible to replicate on Earth. Future lunar missions will take advantage of this natural testing ground to evaluate technologies and materials for deep space exploration, using the moon as a proving ground for systems that must operate in the harsh conditions beyond Earth's protective atmosphere and magnetic field. The relationship between Earth and Moon represents one of the most stable gravitational partnerships in the solar system, a cosmic dance that has persisted for over 4 billion years despite the chaotic interactions that shaped the early planetary system. This stability has provided the foundation for Earth's long-term habitability, creating conditions that allowed life to emerge and evolve over billions of years. The Moon's presence has been a constant influence throughout Earth's history, shaping not just physical processes like tides and climate, but also providing the stable environmental conditions necessary for the development of complex ecosystems and eventually intelligent life capable of contemplating its cosmic origins. As the night deepens and these lunar secrets continue their eternal dance overhead, the Moon maintains its silent vigil, carrying within its ancient structure the story of two worlds bound together by gravity and time. Each phase of its cycle, each gravitational tug on our oceans, each stabilizing influence on our planet's climate represents a continuation of processes that began when the solar system was young and violent. Tonight, as you rest beneath this cosmic guardian, You participate in a relationship forged in the fires of planetary formation and refined over billions of years of gravitational evolution. The moon that watches over your dreams tonight carries the same patient presence that has guided Earth through ice ages and warm periods, mass extinctions and evolutionary radiations, the rise and fall of countless species, and the eventual emergence of conscious beings capable of understanding their place in the cosmic story. In its steady progression across the star-filled sky, our satellite embodies the deep timescales of astronomical processes, reminding us that we are part of a universe where patience and persistence shape worlds, and where the gentle forces of gravity can create partnerships that endure across the vast expanses of cosmic time. The moon's role as Earth's timekeeper extends far beyond the familiar cycle of phases we observe each month. Deep within our planet's geological record, ancient coral reefs preserve evidence of the moon's changing influence over hundreds of millions of years. These fossilized organisms grew in daily and monthly rhythms that reflect the length of days and the frequency of tides in Earth's distant past. By counting the growth rings in these prehistoric corals, scientists have discovered that days were once much shorter and lunar months contained more days than they do today. 400 million years ago, when these corals were alive, a day lasted only about 22 hours, and the moon appeared much larger in the sky as it orbited closer to Earth. The coral record provides a biological clock that spans geological ages, documenting the gradual evolution of the Earth-Moon system through the patient accumulation of calcium carbonate in ancient seas. The moon's influence on biological rhythms extends throughout the natural world, creating cycles that persist even when organisms are removed from direct. Many lunar exposure marine creatures time their reproduction to coincide with specific lunar phases, releasing eggs and sperm into the water during particular tidal conditions that maximize the chances of fertilization and dispersal. These reproductive cycles are so deeply ingrained that they continue even in laboratory settings where animals cannot see the moon or feel its tidal effects. The biological clocks that govern these behaviors appear to be synchronized to the lunar month, suggesting that life on Earth has evolved to take advantage of the moon's predictable rhythms over millions of years of evolution. Coral spawning events represent some of the most spectacular examples of lunar synchronized behavior in nature. On certain nights each year, triggered by the moon's phase and position, entire coral reefs release billions of eggs and sperm simultaneously, creating underwater blizzards of reproductive cells. This synchronized spawning occurs with such precision that marine biologists can predict the exact nights when it will happen, often down to the hour. The timing ensures that reproductive cells from different coral colonies mix in the water column, promoting genetic diversity while maximizing the chances that fertilized eggs will survive their vulnerable early stages. These mass spawning events demonstrate how the moon's gravitational influence has shaped the evolution of reproductive strategies in marine ecosystems. The migration patterns of numerous species follow lunar cycles that help animals navigate across vast distances with remarkable precision. Sea turtles return to their natal beaches to nest during specific lunar phases, using the moon's light to guide their journey from feeding grounds hundreds of miles away. The brightness of the full moon provides illumination for nighttime travel, while its gravitational influence creates tidal conditions that may affect ocean currents and navigation cues. Migratory birds also show sensitivity to lunar cycles, with many species timing their journeys to coincide with particular phases of the moon when atmospheric conditions and celestial navigation cues are most favorable for long-distance flight. The moon's gravitational field creates subtle variations in Earth's shape that affect everything from underground water systems to the behavior of sensitive scientific instruments. As our satellite orbits overhead, it causes the solid Earth to bulge toward the moon by several inches, creating a gravitational tide that moves through the planet's crust like a slow motion wave. This deformation affects groundwater flow patterns, causing water levels in wells and springs to rise and fall in rhythm with the moon's passage. The effect is strong enough that hydrogeologists must account for lunar influences when studying underground water systems and predicting how aquifers will respond to pumping or natural changes in precipitation. The interaction between moonlight and Earth's atmosphere creates optical phenomena that have inspired human culture while revealing details about atmospheric composition and behavior. Moonbows, those rare and ethereal arcs of color that appear in moonlight and mist, form through the same optical principles as solar rainbows, but create a more subtle and mysterious display. The moon's light, already dimmed by reflection from the lunar surface, becomes further filtered by water droplets to produce colors so faint that they often appear white or silver to human eyes. These lunar rainbows typically occur near waterfalls or in areas where fine mist is illuminated by bright moonlight, creating moments of natural magic that connects observers to both terrestrial and celestial beauty. The study of lunar libration reveals that the moon's face is not as unchanging as it appears to casual observers. Due to slight variations in orbital speed and the tilt of the moon's axis, our satellite appears to rock gently back and forth and nod up and down as seen from Earth. This libration allows terrestrial observers to glimpse slightly more than half of the moon's surface over time, seeing around 59% of the total lunar surface, despite the moon's synchronous rotation. The libration occurs because the moon's orbit is elliptical rather than circular, causing it to speed up when closer to Earth and slow down when farther away, while its rotation rate remains constant. This creates a gentle oscillation that reveals slivers of the far side along the moon's edges, like peering around the corners of a slowly swaying sphere. The moon's role in creating Earth's magnetic field variations demonstrates the interconnected nature of our two worlds, even in ways that remain largely invisible. As the moon passes through different regions of Earth's magnetosphere during its orbit, it creates disturbances in the flow of charged particles trapped within our planet's magnetic field. These disturbances generate subtle variations in magnetic field strength that can be detected by sensitive instruments on Earth's surface. The magnetic effects of the moon's passage are most pronounced when our satellite moves through the magnetosphere's tail region, where it creates a wake of disturbed particles that can affect radio communications and satellite operations for hours after the moon has passed. The thermal properties of lunar materials reveal a world where heat moves through rock and soil at speeds that would seem impossibly slow on Earth. During the 2-week lunar day, solar radiation penetrates only a few inches below the surface before the long night begins and temperatures plummet. This shallow heating zone creates thermal waves that propagate downward through the regolith at rates measured in inches per hour, reaching maximum depth just as the surface above begins to cool. The result is a subsurface temperature profile that lags behind surface conditions by days or even weeks, creating thermal inversions where deeper materials remain warmer than the surface long after sunset or cooler than the surface long after sunrise. The moon's influence on atmospheric pressure creates variations so subtle that they require the most sensitive instruments to detect. Yet these atmospheric tides affect weather patterns and air circulation on a global scale. Twice each day, as the moon passes overhead, it pulls on Earth's atmospheric envelope just as it pulls on the oceans, creating pressure waves that ripple around the globe. These atmospheric tides are strongest in the upper atmosphere, where the thin air responds more readily to gravitational forces, but their effects cascade down through all atmospheric layers. The pressure variations are tiny compared to weather-related changes, but they occur with such regularity that meteorologists can predict them with astronomical precision. The discovery of impact glass spherules in lunar samples has provided insights into the violent processes that shaped not just the moon, but all rocky planets' worlds during the solar system's early history. These tiny glass beads formed when meteorite impacts melted lunar surface materials, launching droplets of molten rock high above the surface where they cooled rapidly in the vacuum of space. The spherules preserve the chemical composition of the target materials, while also containing microscopic fragments of the impacting objects, creating natural archives of cosmic collision events. Some glass beads contain multiple generations of impact material, recording sequences of bombardment events that occurred over millions of years as the solar system gradually settled into its current configuration. The Moon's synchronous rotation creates unique lighting conditions that have no parallel on Earth, with terminator regions where the Sun hangs just above or below the horizon for extended periods. Near the lunar poles, some mountain peaks remain in sunlight for months at a time, while nearby crater floors lie in permanent shadow that has persisted for billions of years. These extreme lighting conditions create environments where temperatures can vary by hundreds of degrees over distances of just a few miles, with sun-baked ridges adjacent to permanently frozen valleys. The contrast between these environments is so extreme that they represent some of the most diverse thermal conditions found anywhere in the solar system on a single world. The preservation of ancient impact structures on the Moon provides a complete record of crater formation processes that has been largely erased from Earth's more dynamic surface. The Moon displays every type of impact feature, from simple bowl-shaped craters formed by small objects to complex multi-ring basins created by asteroid-sized impactors. The lack of atmospheric protection and geological activity means that even the smallest impact features remain preserved, creating a natural laboratory for studying collision physics across the full range of impact energies. The relationships between crater size, depth, and target material properties reveal the fundamental physics of high-velocity impacts that occur throughout the solar system. The Moon's exosphere responds to solar activity in ways that create a dynamic, ever-changing atmospheric envelope invisible to human eyes, but detectable by specialized instruments. During solar storms, when the Sun releases enhanced streams of charged particles, the lunar exosphere becomes temporarily denser, as increased bombardment liberates more atoms from the surface. This atmospheric breathing demonstrates the direct connection between the Moon's tenuous atmosphere and the space environment, showing how unprotected worlds respond immediately to changes in stellar radiation. The composition of the exosphere also varies with location and time, reflecting differences in surface materials and the angle at which solar wind strikes different regions. The gravitational interaction between Earth and Moon creates resonance effects that influence the behavior of small objects throughout the inner solar system. Asteroids and comets passing near the Earth-Moon system experience complex gravitational perturbations that can dramatically alter their trajectories, sometimes capturing them temporarily in chaotic orbits around the binary system. These gravitational resonances also affect artificial satellites, with some orbital configurations remaining stable for centuries, while others decay rapidly due to lunar perturbations. The study of these resonance effects helps scientists understand how small bodies move through planetary systems and how gravitational interactions shape the architecture of the solar system over long periods. The Moon's role in Earth's rotational evolution extends beyond simple tidal braking to include effects on the planet's internal structure and heat generation. The gradual slowing of Earth's rotation affects the flow of molten metal in our planet's outer core, potentially influencing the generation of Earth's magnetic field through complex magnetohydrodynamic processes. The changing length of Earth's day also affects atmospheric and oceanic circulation patterns, which in turn influence climate and weather on geological timescales. These interconnected effects demonstrate how the Moon's gravitational influence reaches deep into Earth's interior and affects processes that might seem completely unrelated to celestial mechanics. The chemical evolution of the lunar surface continues today through processes that operate at almost imperceptibly slow rates, but accumulate significant changes over geological time. Solar wind bombardment gradually implants hydrogen and other elements into surface materials, while cosmic ray interactions create new isotopes and break apart existing chemical bonds. Micrometeorite impacts continuously mix and redistribute surface materials, while thermal cycling causes repeated expansion and contraction that slowly fractures rocks and creates new mineral surfaces. These ongoing processes ensure that the Moon's surface is never truly static, but continues to evolve in response to its harsh space environment. The Moon's influence on Earth's ocean chemistry extends beyond simple tidal mixing to include effects on nutrient distribution and marine ecosystem productivity. The vigorous mixing caused by tidal currents brings deep, nutrient-rich waters to the surface while carrying oxygen to deeper layers, supporting marine food chains that depend on this vertical circulation. Without the Moon's tidal influence, many ocean regions would become stratified and depleted of essential nutrients, fundamentally altering marine ecosystems and potentially reducing the ocean's capacity to support life. The Moon's role in ocean mixing also affects the distribution of dissolved gases and helps regulate the exchange of carbon dioxide between the atmosphere and sea. The study of lunar samples has revealed that the Moon experienced periods of renewed volcanic activity much later in its history than previously thought, with some lava flows occurring less than 1 billion years ago. These young volcanic features suggest that the Moon's interior remained partially molten longer than expected, possibly due to gravitational heating from Earth or the decay of radioactive elements within the lunar mantle. The discovery of recent volcanism challenges models of lunathermal evolution and suggests that our satellite may still retain pockets of molten material deep within its interior. This ongoing geological activity, while much reduced from the Moon's early history, demonstrates that our satellite is not the completely dead world once assumed. The Moon's gravitational field contains signatures of ancient impact events that reveal details about the objects that struck our satellite billions of years ago. The mass concentrations beneath major impact basins preserve information about the size, composition, and impact velocity of the objects that created these enormous features. By studying the gravitational anomalies associated with different impact structures, scientists can reconstruct the bombardment history of the inner solar system and understand how the population of impacting objects changed over time. These gravitational fossils provide insights into conditions during the late heavy bombardment and the gradual clearing of debris from planetary formation. The interaction between the Moon's weak magnetic field and the solar wind creates miniature bow shocks and magnetic reconnection events that occur on scales much smaller than similar phenomena at Earth. These micromagnetospheric interactions demonstrate fundamental plasma physics processes in a simplified environment where they can be studied without the complexity of Earth's strong magnetic field and dense atmosphere. The Moon serves as a natural laboratory for understanding how solar wind interacts with magnetized bodies throughout the solar system. From small asteroids to the planet Mercury, these interactions also affect how the solar wind deposits materials on the lunar surface, influencing space weathering processes and the formation of thin surface layers. The Moon's thermal evolution over billions of years has created internal structures that continue to influence seismic activity and heat flow patterns observable today. As the Moon cooled from its initially molten state, different layers solidified at different rates, creating interfaces where contractions and expansions still generate stress and occasional fracturing. The timing of this thermal evolution affected how radioactive elements became distributed within the Moon's interior, influencing heat generation patterns that persist today. Understanding the Moon's thermal history provides insights into how all rocky worlds evolve as they cool from formation, offering a template for understanding planetary evolution throughout the universe. The preservation of volatile materials in lunar, permanently shadowed regions creates archives of solar system chemistry that span billions of years of history. These deposits contain not just water ice, but also frozen carbon dioxide, ammonia, methane, and complex organic compounds that represent samples of materials delivered throughout the solar system's history. The layered structure of these deposits may preserve a record of changing delivery rates and compositions over time, with deeper layers containing materials from earlier epochs, when the solar system was more active and debris-rich. These natural archives provide information about cosmic chemistry that extends far beyond what can be learned from studying meteorites and other samples available on Earth. The Moon's influence on Earth's atmospheric chemistry operates through mechanisms that affect the distribution and concentration of trace gases in ways that cascade through climate systems. Atmospheric tides created by lunar gravity affect how gases mix vertically in the atmosphere, influencing the distribution of water vapor, ozone, and other compounds that affect radiative balance and climate. The Moon's gravitational effects on atmospheric pressure also influence the rates of certain chemical reactions, particularly those involving photodissociation processes that depend on atmospheric density. These subtle chemical effects demonstrate how the Moon's influence extends throughout Earth's environmental systems in ways that are only beginning to be understood. The Moon's surface serves as a cosmic archaeology site, where evidence of early solar system conditions remains preserved in pristine detail. Impact glasses contain samples of impacting objects from throughout the asteroid belt and beyond, while mineral grains preserve isotopic signatures of stellar processes that occurred before the solar system formed. Some lunar materials may even contain pre-solar grains, microscopic relics from other star systems that became incorporated into the solar nebula and eventually found their way to the Moon's surface. These ancient materials provide direct samples of the galactic environment from which our solar system emerged, offering insights into stellar evolution and galactic chemical evolution that cannot be obtained through any other means. The relationship between Earth and Moon creates a unique electromagnetic environment, where both worlds influence each other's interaction with the solar wind and cosmic radiation. Earth's magnetosphere extends far enough to sometimes encompass the Moon's orbit, providing partial protection from solar storms and cosmic ray bombardment during certain phases of the lunar cycle. When the Moon passes through Earth's magnetotail, it experiences a different radiation environment that affects surface chemistry and exosphere composition in subtle but measurable ways. This variable electromagnetic environment creates different space weathering conditions across the Moon's surface, depending on orbital position and solar activity levels. The Moon's role in shaping Earth's early atmosphere may have extended beyond tidal effects to include direct delivery of volatile materials through impact processes. During the late heavy bombardment, when both Earth and Moon were heavily cratered by asteroid and comet impacts, materials ejected from lunar impacts could have reached Earth's atmosphere, potentially contributing to atmospheric composition and chemistry. While most lunar impact debris would have been lost to space, some fraction may have been captured by Earth's gravity and added to our planet's volatile inventory. This cross-contamination between worlds demonstrates the interconnected nature of planetary evolution in the early solar system. The study of lunar dust electrification has revealed that the Moon's surface develops strong electrostatic charges that affect how materials behave in the airless environment. During lunar daylight, photoelectric effects cause the surface to develop positive charges, while shadowed regions accumulate negative charges, creating electric fields strong enough to levitate dust particles above the surface. This electrostatic levitation may transport fine materials across the lunar landscape, redistributing surface compositions and creating the levitating dust clouds that Apollo astronauts reported seeing along the horizon during lunar sunrise and sunset. The electrification processes also affect how spacecraft and equipment interact with the lunar surface, creating engineering challenges for future missions. The Moon's influence on Earth's solid tides affects underground water systems, earthquake timing, and even the behavior of sensitive scientific instruments that must account for the regular flexing of Earth's crust. Deep underground mines and tunnels experience measurable deformation as the solid Earth tide passes through, affecting ventilation systems and structural stability. The timing of some earthquake events shows weak correlations with tidal stress patterns, suggesting that lunar influences may provide the final trigger for seismic events that are already close to failure. These solid Earth effects demonstrate how thoroughly the Moon's gravitational influence permeates our planet, reaching into the deepest accessible regions of Earth's crust and affecting processes that might seem completely removed from celestial mechanics. The Moon's preservation of impact melt rocks provides samples of materials that experience the most extreme conditions possible during planetary formation. These rocks formed when massive impacts generated temperatures and pressures comparable to those in Earth's deep interior, creating unique mineral assemblages and textures not found in other geological processes. The shock metamorphism preserved in lunar impact rocks reveals details about the physics of hypervelocity collisions and the conditions that existed during the solar system's most violent period. These natural experiments in extreme physics provide insights into planetary formation processes that cannot be replicated in terrestrial laboratories. The Moon's role as a gravitational anchor for Earth extends to stabilizing not just axial tilt, but also the complex wobbles and precessions that affect climate on multiple timescales. Without the Moon's stabilizing influence, Earth's rotational axis would wander chaotically over periods of thousands to millions of years, creating unpredictable climate variations that would make ice age cycles far more irregular and extreme. The Moon's presence constrains these variations to small, predictable oscillations that allow Earth's climate system to develop long-term stability and predictability. This gravitational anchoring has been crucial for the evolution of complex life forms that depend on relatively stable environmental conditions over evolutionary timescales. As we continue our gentle drift through these lunar mysteries, the Moon above maintains its patient watch, carrying within its ancient structure the accumulated history of 4.5 billion years of cosmic evolution. Each crater on its surface marks a moment of cosmic violence, while each handful of regolith contains atoms that have journeyed from the heart of our star to find their final resting place in the lunar soil. The water ice, hidden in polar shadows, preserves chemical signatures from the earliest epochs of solar system formation, while the Moon's gradually receding orbit continues the slow evolution of the Earth-Moon system that began with a collision of worlds and will continue until the stars themselves grow old. Tonight, as you rest in the gravitational embrace of this cosmic partnership, you participate in a relationship that connects you to the fundamental forces that shape planets and the patient processes that create the stable environments where life can flourish and consciousness can emerge to contemplate its place in the vast, interconnected web of cosmic time. The Moon's gravitational pull creates phenomena so subtle they escape casual notice, yet profoundly shape our world in ways that extend far beyond the rise and fall of tides. Deep beneath the surface of our oceans, the Moon's influence drives massive circulation systems that carry nutrients from the abyssal depths to sunlit surface waters where life flourishes. These deep currents, powered by the same forces that lift our seas twice daily, transport heat and dissolved gases across entire ocean basins, moderating global climate patterns and maintaining the chemical balance that supports marine ecosystems. Without this lunar mixing, our oceans would stratify into lifeless layers, with oxygen-rich surface waters separated from nutrient-rich depths by barriers that few organisms could cross. The Moon's role in atmospheric dynamics creates pressure waves so gentle they require the most sensitive instruments to detect. Yet these invisible tides ripple through our entire atmospheric envelope twice each day. As our satellite passes overhead, it pulls on the gaseous layers that surround Earth, just as it pulls on liquid water, creating systematic pressure variations that influence wind patterns and weather systems on scales both local and global. These atmospheric tides are strongest in the upper reaches of our atmosphere, where thin air responds more readily to gravitational forces, but their effects cascade downward through every layer, subtly influencing the great circulation patterns that distribute heat and moisture around our planet. The study of ancient tree rings and coral growth bands has revealed that the Moon's influence on Earth has been slowly evolving over geological timescales, leaving traces in the growth patterns of organisms that lived millions of years ago. These biological archives show that days were once much shorter, and lunar months contained more daily cycles than they do today, evidence of the gradual slowing of Earth's rotation and the Moon's steady recession from our planet. The patterns preserved in fossilized wood and calcium carbonate structures demonstrate how the Moon's changing influence has affected tidal ranges, seasonal patterns, and the very rhythm of life on Earth throughout natural history. Within the Moon's permanently shadowed regions, temperatures remain so constant and so cold that they create natural laboratories, where the laws of chemistry and physics operate under conditions found nowhere else in the inner solar system. These perpetually dark valleys, chilled to temperatures that approach absolute zero, preserve materials that would decompose or sublimate away in any other environment. The ice deposits hidden within these shadows contain not just frozen water, but also carbon dioxide, ammonia, and complex organic molecules that represent chemical fossils from the solar system's earliest epochs. Each layer in these frozen archives tells part of the story of cosmic evolution, preserving samples of materials that fell from space over billions of years. The interaction between solar radiation and the Moon's surface creates ongoing chemical reactions that slowly transform the composition of lunar materials through processes that have no equivalent on Earth. When high-energy particles from the Sun strike oxygen-bearing minerals in the lunar regolith, they can directly create water molecules through reactions that occur grain by grain across the entire sunlit surface. This process happens continuously, but at rates so slow that it takes thousands of years to produce measurable amounts of water, demonstrating the patient timescales on which cosmic chemistry operates in the vacuum of space. The Moon's weak magnetic field, though vastly diminished from its ancient strength, still creates localized effects that influence how space weather interacts with specific regions of the lunar surface. These magnetic anomalies act like miniature umbrellas, partially deflecting the solar wind and creating unique microenvironments where surface materials weather differently than in surrounding areas. The patterns of magnetic shielding create a complex mosaic of surface conditions that vary from place to place, with some regions aging more slowly than others due to their partial protection from the constant bombardment of charged particles. Modern laser ranging experiments, which bounce light beams off reflectors left on the Moon by Apollo astronauts, can measure the Earth-Moon distance with such precision that they detect changes smaller than the width of a human hair. These measurements reveal not just the Moon's gradual recession, but also subtle variations in Earth's rotation rate, the effects of melting ice sheets on our planet's shape, and even the influence of atmospheric pressure changes on Earth's gravitational field. The Moon serves as a cosmic surveying benchmark, allowing scientists to track changes in Earth's physical properties with extraordinary accuracy. The discovery of glass beads in lunar samples revealed evidence of ancient fire fountains that once erupted from the Moon's interior, with spectacular displays of molten droplets arcing high above the surface. These tiny spheres formed when volcanic gases propelled molten rock into the vacuum of space, where it cooled rapidly into perfect glass spherules that preserve the chemical signature of the Moon's deep interior. Some of these glass beads contain bubbles of ancient volcanic gases, providing actual samples of the Moon's primordial atmosphere that existed briefly during periods of intense geological activity. The Moon's influence on biological rhythms extends throughout the natural world in ways that persist even when organisms are removed from any direct exposure to lunar light or gravitational effects. Many marine creatures time their reproductive cycles to coincide with specific lunar phases, releasing eggs and sperm into tidal currents that provide optimal conditions for fertilization and larval dispersal. These behavioral patterns are so deeply ingrained that they continue in laboratory settings where animals cannot see the Moon or experience tidal changes, suggesting that lunar rhythms have become encoded in biological clocks through millions of years of evolutionary adaptation. The thermal properties of lunar materials create temperature patterns that defy earthly intuition, with heat moving through rock and soil at rates that would seem impossibly slow in terrestrial environments. During the 2-week lunar day, solar energy penetrates only inches below the surface before the long night begins, and temperatures plummet by hundreds of degrees. This shallow heating creates thermal waves that propagate downward through the regolith like slow-motion ripples, reaching maximum depth just as the surface above begins its long cooling phase. The Moon's gravitational field contains subtle irregularities that reveal hidden mass concentrations buried beneath impact basins, dense regions where ancient collisions either excavated material from deep within the Moon or deposited the remnants of massive impacting objects. These gravitational anomalies affect spacecraft orbits in measurable ways, creating three-dimensional maps of the Moon's internal structure that complement surface observations and seismic data. The patterns of buried mass tell stories of the most violent events in lunar history, preserving evidence of impacts so massive they reshaped the Moon's internal architecture. The preservation of cosmic ray tracks in lunar crystals provides a record of high-energy particle bombardment that spans millions of years, creating microscopic damage trails that can be analyzed to understand the radiation environment of space over geological timescales. These particle tracks accumulate grain by grain in surface minerals, building up radiation damage that serves as a cosmic dosimeter, recording the intensity of galactic cosmic rays and solar particle events. The tracks also provide information about how long specific rock samples have been exposed at the lunar surface, creating chronometers that measure exposure ages with remarkable precision. The Moon's synchronous rotation creates lighting conditions at the lunar poles that have no parallel anywhere else in the solar system, with some mountain peaks remaining in continuous sunlight for months, while nearby crater floors lie in permanent darkness. These extreme lighting contrasts create temperature variations of hundreds of degrees over distances of just a few miles, generating thermal stress patterns that continuously fracture and reshape the landscape through cycles of expansion and contraction. The boundaries between illuminated and shadowed regions become zones of perpetual geological activity driven entirely by thermal forces. Recent analysis of lunar samples has revealed the presence of native metals, including iron, copper, and even traces of gold, created by the reduction of metal oxides under the extreme conditions of meteorite impact. These metallic deposits form when the oxygen in mineral compounds is stripped away by the intense heat and chemical environment of hypervelocity collisions, leaving behind pure metals that would quickly oxidize away in Earth's oxygen-rich environment. The lunar surface serves as a natural smelter where cosmic impacts have been producing refined metals for billions of years. The Moon's exosphere responds dynamically to changes in solar activity, expanding and contracting as the intensity of solar wind bombardment varies with solar storms and the 11-year solar cycle. During periods of enhanced solar activity, increased particle bombardment liberates more atoms from the lunar surface, temporarily thickening the 10 in exiguous atmospheric envelope. These variations, how the Moon interosphere density, affect acts with charged particles and electromagnetic fields, creating a feedback system where solar activity directly influences lunar atmospheric conditions. The gravitational interaction between Earth and Moon creates resonance effects that influence the motion of small objects throughout the inner solar system, with some asteroids and comets becoming temporarily captured in complex orbital dances around the Earth-Moon system. These gravitational resonances can persist for thousands of years, creating populations of quasi-satellites and co-orbital objects that follow intricate trajectories shaped by the combined gravitational fields of both worlds. The study of these resonance patterns helps scientists understand how gravitational interactions sculpt the architecture of planetary systems over time. The Moon's role in Earth's magnetic field evolution may extend beyond simple gravitational effects to include influences on the convection patterns that generate our planet's protective magnetosphere. The tidal forces that flex Earth's interior may affect the flow of molten metal in our planet's outer core, potentially influencing the dynamo processes that create and maintain Earth's magnetic field. These magneto-hydrodynamic interactions operate on timescales of thousands to millions of years, contributing to the long-term evolution of Earth's magnetic protection against cosmic radiation. The chemical weathering of lunar rocks occurs through processes completely different from terrestrial weathering, with solar wind implantation and cosmic ray bombardment gradually altering mineral compositions over millions of years. This space weathering creates thin surface layers with properties dramatically different from the underlying bedrock, generating optical effects that change how different regions reflect sunlight. The weathering process also creates microscopic glass coatings on individual mineral grains, giving aged lunar surfaces their characteristic dark appearance. The Moon's gravitational influence on Earth's rotational axis creates subtle but measurable effects on the planet's shape, causing our world to bulge slightly toward our satellite as it orbits overhead. This deformation is so small that it amounts to only inches across Earth's entire diameter, yet it demonstrates how thoroughly the Moon's presence affects our planet's physical structure. The bulge migrates around Earth as the Moon orbits, creating a gravitational wave that propagates through the solid planet at the speed of seismic waves. The discovery of impact breccias in lunar samples has revealed that the Moon's surface has been repeatedly pulverized and reconsolidated by countless meteorite impacts, creating rock formations that contain fragments from impacts spanning billions of years. These breccias serve as natural archives of bombardment history, with individual rock samples containing pieces of materials from dozens of different impact events. The complex textures and compositions of these rocks tell stories of cosmic violence and recovery that played out over geological time. The Moon's thermal evolution has created internal temperature gradients that still influence geological processes today, with some regions of the interior remaining warm enough to generate occasional moonquakes when tidal stresses exceed the strength of fractured rock. These seismic events occur most frequently when the Moon passes closest to Earth in its elliptical orbit, demonstrating that gravitational forces continue to shape lunar geology even after billions of years of cooling. The patterns of seismic activity reveal details about the Moon's internal structure and the distribution of fractures within its rocky layers. The interaction between the Moon's gravity and Earth's atmospheric tides affects the distribution of gases at different altitudes, influencing everything from ozone chemistry to the behavior of the ionosphere. These atmospheric effects operate on scales both large and small, from global circulation patterns that distribute heat and moisture to local phenomena that affect radio wave propagation and satellite communications. The Moon's atmospheric influence demonstrates how gravitational forces can reach across the vacuum of space to affect the most tenuous parts of planetary environments. The preservation of solar wind particles in lunar regolith has created a vast archive of the Sun's activity spanning millions of years, with different layers of soil containing particle populations that reflect changing solar conditions over geological time. This record extends far beyond human observations of solar variability, providing insights into long-term stellar evolution and the history of space weather throughout the inner solar system. The isotopic compositions of embedded solar wind atoms reveal how the Sun's nuclear processes and magnetic field behavior have changed over cosmic time. The Moon's role in stabilizing Earth's climate extends beyond axial stabilization to include effects on ocean circulation patterns that distribute heat around the globe and regulate the exchange of gases between sea and atmosphere. The vigorous mixing caused by tidal currents brings nutrient-rich deep water to the surface while carrying oxygen to the ocean depths, supporting marine ecosystems that form the foundation of global food webs. Without the Moon's tidal influence, ocean stratification would reduce biological productivity and alter the capacity of seawater to absorb carbon dioxide from the atmosphere. The study of lunar magnetic anomalies has revealed that our satellite once possessed a global magnetic field comparable in strength to Earth's current field, generated by convection in a molten iron core during the Moon's early geological history. The gradual decay and eventual disappearance of this ancient magnetosphere marked a fundamental transition in lunar evolution, from a geologically active world with internal heat sources to the quiet, cold body we observe today. Paleomagnetic records preserved in lunar rocks provide a timeline for this magnetic field evolution that extends back over 4 billion years. The Moon's gravitational field affects the orbits of artificial satellites and space debris in Earth orbit, creating complex perturbations that must be carefully calculated for long-term mission planning. Some orbital configurations remain stable for centuries due to gravitational resonances with the Moon, while others decay rapidly as lunar perturbations gradually alter satellite trajectories. These orbital dynamics affect everything from communication satellites to space stations, requiring constant monitoring and occasional adjustments to maintain desired orbital parameters. The interaction between cosmic dust and the Moon's electrostatic environment creates phenomena that would seem magical in any earthly context, with fine particles levitating above the surface during the transition between lunar day and night. As the sun sets or rises at any location on the Moon, changing patterns of photoelectric charging create electric fields strong enough to lift dust grains and transport them across the landscape. Apollo astronauts reported seeing these levitating dust clouds as faint glows along the horizon during lunar twilight, creating temporary atmospheric phenomena in a world that otherwise lacks any significant atmosphere. The Moon's influence on Earth's solid tides affects underground water systems and geological processes in ways that cascade through terrestrial environmental systems. Deep aquifers experience pressure variations that follow lunar cycles, while the timing of some seismic events shows weak correlations with tidal stress patterns. These solid Earth effects demonstrate how the Moon's gravitational reach extends deep into our planet's interior, affecting processes that might seem completely disconnected from celestial mechanics, yet respond to the subtle but persistent influence of our cosmic companion. The chemical composition of permanently shadowed regions reveals a complex mixture of materials delivered over billions of years by comets, asteroids, and solar wind particles, creating natural laboratories where primordial solar system chemistry remains preserved in pristine condition. These deposits contain organic compounds, noble gases, and isotopic signatures that provide direct samples of the cosmic environment from which Earth and Moon formed. Each handful of shadowed regolith represents a time capsule containing materials that span the entire history of the solar system, from its earliest chaotic epochs to the more stable conditions that prevail today. As our gentle journey through these lunar mysteries continues, the Moon above carries forward its patient role as Earth's companion and guardian, maintaining the gravitational partnership that has shaped both worlds for over 4 billion years. Within its ancient craters lie samples of cosmic violence that forged the inner planets, while its hidden ice deposits preserve chemical memories of the solar system's youth. The same tidal forces that move our oceans continue to slow Earth's rotation and push the Moon gradually away, writing the next chapters in a cosmic story that began with collision and fire and continues with the quiet persistence of gravitational forces operating across the vast scales of astronomical time. Tonight, as you rest in the invisible embrace of lunar gravity, you participate in this cosmic relationship that connects you to the fundamental processes that create stable worlds and the patient evolution that allows consciousness to emerge and contemplate its place in the endless dance of matter and energy that fills the universe. The Moon's surface bears witness to the most ancient bombardment events preserved anywhere in the solar system, creating a fossil record of cosmic violence that extends back to the very beginning of planetary formation. Each crater tells a story of hypervelocity impact, from the smallest pits created by microscopic dust grains to the enormous multi-ring basins carved by asteroid-sized objects that struck with the force of billions of nuclear weapons. The largest of these impact structures, visible as dark patches to the naked eye, represent collisions so massive they crack the Moon's crust, and allowed molten rock from deep within to flow across hundreds of miles of surface, creating the smooth volcanic plains that form the familiar features we see in the lunar face. The preservation of these impact records occurs because the Moon lacks the geological processes that continuously reshape Earth's surface, without plate tectonics to recycle crustal materials or atmospheric weathering to erode surface features. Every impact remains frozen in time, like a photograph of cosmic collision. The smallest craters, formed by meteoroids no larger than grains of sand, nestle within larger structures created by house-sized objects, which in turn lie within the enormous basins excavated by mountain-sized impactors. This nested hierarchy of destruction creates a complete catalogue of bombardment intensity that scientists can read like pages in a book of solar system history. Within the regolith that blankets the lunar surface, microscopic glass spherules preserve the exact moment of impact in crystalline detail. These tiny beads formed when the intense heat of collision melted surface rocks, launching droplets of molten material high above the Moon where they cooled rapidly in the vacuum of space. Each spherule contains microscopic fragments of both the target rocks and the impacting object, creating natural samples of materials that originated throughout the asteroid belt and beyond. Some glass beads show evidence of multiple impact events, with older spherules remelted and reformed by later collisions, recording sequences of bombardment that span millions of years. The Moon's far side reveals a landscape even more heavily scarred than the familiar near side, displaying impact structures that date back to the earliest epochs of solar system formation. This hidden hemisphere remained completely unknown until Soviet spacecraft first photographed it, revealing a rugged terrain dominated by ancient craters overlapping in complex patterns that tell stories of primordial chaos. The far side's thicker crust preserved these ancient scars because volcanic activity was less able to fill and erase the impact basins, leaving intact a record of bombardment from the solar system's most violent period. The chemical signatures preserved in impact glass reveal details about the population of objects that struck the Moon during different periods of its history. Early impacts show evidence of water-rich objects, possibly comets from the outer solar system that brought volatile materials to the inner. Their formation. Later impacts reflect planets during a different population of drier, rocky objects, more typical of the asteroid belt between Mars and Jupiter. This changing composition of impactors provides insights into how the solar system evolved from its initial chaotic state to the more organized structure we observe today. Deep beneath some of the Moon's largest impact basins lie gravitational anomalies that reveal hidden concentrations of dense material, possibly the remnants of the massive objects that created these enormous structures. These buried masses, detected by their influence on spacecraft orbits, suggest that some impactors were so large they survived the collision process and became incorporated into the Moon's internal structure. The gravitational maps created by these measurements show that the Moon's interior is far from uniform, containing density variations that reflect the complex history of cosmic bombardment and internal differentiation. The study of shock metamorphism in lunar samples has revealed the extreme conditions that existed during the most violent impact events, with pressures and temperatures that exceeded those found in Earth's deepest interior. These conditions created unique mineral phases that can only form under the extreme circumstances of hypervelocity collision, providing natural experiments in high-pressure physics that cannot be replicated in terrestrial laboratories. The shock effects preserved in lunar rocks demonstrate that impacts were capable of completely transforming surface materials, creating new mineral assemblages and textures that bear little resemblance to their original forms. The timing of major bombardment events, determined by dating impact glass and shocked minerals, reveals that the Moon experienced periods of intense cratering, interspersed with quieter epochs when fewer large objects struck its surface. The most intense period, known as the Late Heavy Bombardment, occurred between 4 and 3.5 billion years ago, when asteroid-sized objects regularly struck the moon with devastating force. This bombardment may have been triggered by gravitational instabilities in the outer solar system that sent populations of large objects careening toward the inner planets. And now, as our moonlit journey draws to its gentle close, these 100 lunar secrets settle into the quiet spaces of your mind like stardust on an ancient surface. We've wandered together through 4.5 billion years of cosmic history, from the violent collision that birthed our celestial companion to the hidden ice deposits that may one day sustain human dreams among the stars. We've discovered how this silver guardian shapes our tides and stabilizes our seasons, how it preserves the fossil record of solar system bombardment, and how its patient gravitational embrace continues to guide Earth through the vast choreography of space and time. The moon that watches over you tonight carries all these mysteries within its ancient structure, a cosmic library written in rock and ice, in gravitational whispers and magnetic memories. Rest now, knowing that above you drifts this eternal companion, forever linked to our world by forces older than life itself, forever carrying forward the gentle story of two worlds dancing together through the endless night. Forever carrying forward the gentle story of two worlds dancing together through the endless night.